use in chemistry, stoichiometry. It might sound intimidated at first, but I promise you it's just a kind of version of recipe math. Yeah, stoichiometry helps us answer questions as how much product I will produce, how much reactant do I need, and what happens if some of my compounds runs out. So whether you were baking cookies or filling a rocket or analyzing pollution, so stoichiometry gives you the number behind the chemical reactions. It's all about mole ratios, balanced equations, conversions, moles to grams. By the end of these units, you will be able to use chemical reactions to find or calculate mass of a product or moles. And the next part of this chapter, you're gonna also learn how to calculate percent yield through the limiting reactants and the production, like actual yield, theoretical yield. So will be so fun. I love this part, and I'm pretty sure that you're gonna love as well. So let's start our journey over here. So let's start with this reaction here, the balanced chemical equation for fossil fuels. Combustion reaction provide the exact relationship between the amount of fossil fuels, like in this case is octane, which is a part of gasoline, and the amount of carbon dioxide. Oh, let me get back because I was just trying to grab my pen over here. So I know that 2 moles of the octane will produce 16 moles of carbon dioxide, right? So stoichiometry is the math of chemistry and tells us how much product forms from a given amount of reactant. For example, burning octane produces a predictable amount of carbon dioxide. This is how scientists estimate emissions from fuel use. The coefficient in a chemical reaction specifies the relative amounts in moles of each of the substances involved in the reaction. Here I can say 2 molecules of octane will react with 25 moles of oxygen to produce 16 moles of CO2 and 18 moles of water. I can say molecules or moles. So, and I can write down 2 moles per 25 moles, 16 moles, 18 moles, and identify your compounds, molecules, right? 2 moles of octane, 25 moles of oxygen, 16 moles of CO2, and 18 moles of water. And imagine if I double. Instead of 2 moles of octane, I have 4 moles of octane. So, and you should be fine to predict like how many moles of oxygen do I need if I have 4 moles of octane. So if I double, right? So of course I need to double this as well, so going to be 50 moles of oxygen, because I know that 2 moles I will need 25. So how I got that? So I know if I have 4 moles of octane, right? And I know that 2 moles of octane are needed to react with 25 moles of oxygen, right? So we're going to cut this and this. So I know this will be 2 times 25, 50 moles of oxygen. Pretty easy, right? So it's like making pizza. For example, if your recipe needs 2 cups of cheese per pizza, right? And they need 5 ounces of tomato sauce and 1 crust to produce 1 pizza, you know that we can represent this relationship, right? Can be expressed mathematically. So 1 crust per 5 ounces of sauce per 2 cups of cheese per 1 pizza. So we can compare the amount of pizza that can be made from 6 cups of cheese. So if I have 6 cups of cheese, so I know that 2 cups of cheese, I will produce 1 pizza. If I have 6, look at this, 6 divided by 2 over here, 3 pizza. Good? But in stoichiometry, when you have a chemical reactions, I will give here golden rule. It's not so linear because normally when you talk about stoichiometry, So we can start with grams or liters or volume. So what are you gonna do? Liters are volume. So I can have to work with the gas, and I have to work with the equation of the gas to find moles, right? So what's most important here is you must go through moles to connect any two substances in a chemical reaction. So this is why I brought this diagram over here. So, and I have, imagine if I start with grams, so I will convert to moles first through the molar mass of the compound to find moles. And with the chemical equation ratio, I can find the moles of another reactant or a product. So what is that? The chemical equation ratio. This is a set of the coefficients in the balanced equations that shows the proportional relationship between the substance. Exactly what you saw over there with me. So in the previous slide. So I have 1 mole of methane that will react with 2 moles of oxygen to produce 1 mole of CO2 and 2 moles of water. Good? Those numbers here in front. So if I'm working the oxygen and then want to know how many moles of water I'm going to produce, I have a 2 for 2. That will be my chemical equation ratio. So let's start moles to moles over here. So if the moles to moles will be easy. The only thing I need is the chemical equation ratio. So when you use the ratio from the balanced chemical equation and the same way that we use and the ratio from pizza recipe, remember? So the ratio acts as a conversion factor between the amount in moles of the reactant, octane in this case, and the amount in moles of product CO2. So we have 2 moles of octane to 16 moles of CO2. So to do this and to test this, let's gonna start burning 22 moles of octane over here. And they ask how many moles of CO2 are gonna form. I know that 2 moles of octane will produce 16 moles of CO2. Now I need to know how many moles of CO2 will be produced if you have a 22 moles. So I'm gonna use the equation, chemical equation ratio, 16 CO2 for 2 moles of octane. So I can cancel out over here, multiply by 16 divided by 2, and I'm going to have 176 moles of CO2. So I know that the combustion of 22 moles of octane adds 176 moles of carbon dioxide to the atmosphere. So let's test your knowledge over here in terms of moles and the mole ratio. So use the balanced equation for the combustion of octane to determine how many moles of water molecule are produced by the combustion of 22 moles of octane. Good. You want 22 moles, right? This is what you have of octane. And you know that 2 moles of octane will produce 18 moles of water. So I can cut this off. So if I divide this, would be 9 times 22 will be 198 moles of water. Pretty simple, right? The same thing that we did with the pizza, we're gonna do over here with chemistry. So, but can be tricky when you work with the grams, because in real life we measure substance in grams. So we convert grams to moles, and then we use moles, the mole ratio. So the first step will be this, using molar mass to find moles, and then we're gonna use the chemical equation ratio, and then we convert back to grams if you need through the molar mass of the reactant or product B. So let's see this example over here. This example over here says that the world burned the equivalent of 3.7 times 10 to the 10th barrels of petroleum in 2017. we can estimate the mass of CO2 produced based on the flow chart over here, the same type of flow chart that I showed you before. So we have the mass of A. So we're going to find the amount of A to the molar mass of A. Then with the chemical equation ratio, we're going to find the amount of B in moles. And then we're going to find the mass of B if you have the molar mass of B. So let's see the example. So let's start the calculations over here. First, let's organize. So we know the molar mass of each of the molecules over here. So we know that we have how we calculate the molar mass. So we go to periodic table, find the atomic mass of each element, for example, the carbon times 8, and add with the 18 times the atomic mass of hydrogen. Add all together, and you have 114.22 grams per mole, and I'm going to do the same thing for CO2. I know the stoichiometric ratio that 2 moles of octane will produce 16 moles of CO2. First step, convert this to grams. So to convert this to moles, so I have grams to moles. I'm using here molar mass to find moles of octane. So because they're going to cancel out grams and they're going to stay with moles, okay? And then I'm using here the mole ratio. So 16 per 2. So here moles of CO2 is up here because this is what I want to find, and this one I want to cancel out. So we can do step by step or do direct like me doing here. So 4 times 10 to 25 times 1 times 16 divided by the product of 114.22 times 2. And they're going to have the moles of CO2. But problem is asking me how many grams. So to find grams, I'm going to use the molar mass, but the molar mass of CO2. So grams is what I want, so I'm going to come up here because here you want to cancel out moles of CO2. And we're going to have 1.2 times 10 to the 16 grams of CO2. This is what you're going to produce if you burn 4.0 times 10 to the 50 grams of octane. Good? Let's keep testing your understanding over here. So in this problem here, under certain conditions, sodium reacts with oxygen to form sodium oxide according to this reaction. So which of the following images best represent the amount of sodium? So I want to know the amount of sodium required to completely react with all the oxygen in the above diagram. So here I have 3 moles of oxygen, right? 1, 2, 3. Remember, oxygen is diatomic molecule. This is why it's O2. So I know that 1 mole of O2 needs 4 moles of sodium, right? So I can use this as conversion factor. So I have 3 moles of oxygen. So if I have 1 mole of oxygen, I know that I need 4 moles of sodium. So we're going to cut this, and this 4 times 3 is 12. So we're going to need 12 moles of sodium. So when I have 12 moles of sodium, I have 3, 6, and here 6, so 12. Here I have 2, 4, 6, 8. Here I have 4, and here I have only 6. So my answer is C. Okay? So I ask you to stop your video and try by yourself. This one. So here is, we have a generic chemical equation, and let's circle represent molecules of A. Okay, so this is the circle, and squares will be the B. So the diagram shows above represent the amount of B available. Which diagram in the reaction option accurately represents the amount of A necessary to completely react with B? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 11, 12B, right? So I know that let's convert this is 12 moles of B. I know that 3 moles of B requires just 1 mole of A, right? 3 per 1 over here. So we're going to cut B and B. So 12 divided by 3 is 4. I will need 4 moles of A. So here I have 4, 2, here I have 3, 6, 8, 2, 4, and 6. So the answer is 8. Good? Okay, and you might ask yourself like, okay, this is good, it's pretty easy, so I can see it, I can count. But how that works in chemistry for real, and the reactions, and how am I gonna do? One more problem over here. Several brands of antacids tablets use aluminum hydroxide to neutralize excess acid in your stomach. So how many moles of aluminum hydroxide are required to produce 6 moles of water? Just stop your video and try by yourself. So I know that I have a balanced reaction over here, right? So I have a 3 hydrogen plus 3, I have a 6 hydrogen. 3 times 2 is 6 hydrogen. And I have a 1 aluminum, 3 chlorines over here, and 3 oxygens over here, 3 oxygens over here. So it's a perfect balance. So I know that 1 mole of aluminum hydroxide will be required to produce only 3 moles of water. If I have a 6, so if I have a 6, I'm gonna use my mole ratio as my conversion factor over here. I can cut off this, cancel out the units moles of water, and I have moles of aluminum hydroxide. So I need 2 moles of aluminum hydroxide to produce 6 moles of water. Another question. How many moles of hydrochloric acid will 0.25 moles of aluminum hydroxide neutralize? I know that 1 mole of aluminum hydroxide will neutralize 3 moles of hydrochloric acid. So how am I going to do it here? So I have 0.25. Know that 1 mole, see, again, using the mole ratio, the chemical equation ratio here. So I'm going to cancel out this over here, and I'm going to find 0.75 moles of hydrochloric acid. Good? Okay, so I gave you moles, and you must ask yourself, so if I have grams instead moles? Okay, so here, one more question. So we have here this reaction, and you have a mass of oxygen, and they are asking you the mass of aluminum that you need to complete the reaction. That's a hint for you. First, you need to convert mass to moles, and you will need the moles ratio of the equation. So please always check if the reaction is well balanced, and then you find the numbers of moles. So you have grams, use a molar mass to find the moles of oxygen. Through the chemical equation ratio, you're gonna find the moles of aluminum. Good? So first step, the one that you didn't do in the last problem, is to convert to moles. And then you use the mole ratio. Okay? So we have the molar mass to find the moles of oxygen. And then we have the equation ratio to find the moles of aluminum. Good? If they ask you, okay, I need grams of aluminum now, the only thing that you would need here is the molar mass of aluminum to find grams. Okay? So there will be more videos to practice those kind of problems in stoichiometry, and I really suggest that you watch those videos. And the next part of this chapter, we're going to talk about limiting reactant, actual and theoretical yield, and percent yield. For now, that's it. That's all. Bye for now.